some wonderful pictures for you every month over on the table over there. You can pick one up. Tonight's picture is the supernova remnant SN1006, which you might know how to interpret that is a supernova that we've seen in, believed to have exploded 1,000 years ago, okay, 1006. Now this one, if you look in the back, you can see it's just a red ribbon, okay? It's a wonderful picture of a red ribbon, okay, but if you turn on the back, you can see a composite of visible light and X-ray light that shows you the full bubble of this supernova remnant and how this ribbon is just one little piece of the supernova remnant, and lots of explanation on the back. As I said, if you didn't get it on the way in, grab it on the way out. Okay, so tonight's talk, is this working? It's not, there it's working. Okay, Dawn, a journey to the early solar system with Dr. Lucy McFadden from the Goddard Space Flight Center, and I've been so excited to get you here, so this is going to be lots of fun. Upcoming, we have January 5th. Vanessa Thomas, Max Muchler, and Rosa Diaz will be they went and were on the White House lawn with their telescopes for White House Astronomy Night this year, and they will tell you their experiences. Actually, I see two of them in the audience. I don't know if Rosa's here, but I see Vanessa in the audience back there. In February, the Southern Skies Astronomy in Chile. Mia Bovel here in Space Telescope. Chile has some amazing telescope observatories. Just amazing stuff there. So this is going to be really cool to see all of the number of world-class astronomical observatories in Chile is maybe bigger than most any country out there. And then in March, we have John Debes. He gave us a Halloween talk that had this spooky title, and he decided, well, I'm going to keep with the spooky titles, even though it's not on Halloween. So on March 1st, he will be talking about planetary tales from the stellar crypt, exoplanets, surviving the death of their host star. So we've got a Tales from the Underworld in March. If you would like to see all of the details, you can go to our website. We have this Go link, HubbleSite.org, Go Talks. If you just search Hubble Public Lecture, you should find this page. We have a list of the upcoming lectures over here. We have the archive of the lectures down here. If you want to see lectures back to 2005 in our webcast, they are available for you there, as well as lots of other information. Our announcements are available by signing up at a website called maillist.stsci.edu. You click on Public Lecture Announce and provide your email address. If you have problems with that, you can also just hand me your email address when you're here at the talk, and I can get you signed up for the public lecture. If you would like to ask questions of me or the speaker or provide suggestions, you can send them to publiclecture@stsci.edu. You can even use this as a way to sign up for our mailing list, because if you send an email there, I'll have your return address and we can add you to the mailing list. We're also available on social media, Facebook, not one, but two Twitter accounts, Google Plus and Pinterest, and maybe a few more that I don't know about, okay? So if you're in social media, you can do that. Myself, I have a blog, Hubble's Universe Unfiltered. I'm also on Facebook, Google Plus, and Twitter, although I'm not incredibly active on those, so don't expect 17 tweets a day from me. If you get one, I'm doing well. All right, across the street we have the Maryland Space Grant Observatory. And you'll notice that it always says weather permitting on the slide, but we have the big red no symbol because the weather isn't permitting today. So we will not be going across the street. If you do want to use the Maryland Space Grant Observatory, go to md.spacegrant.org. They have public nights every Friday night, I believe, and you can find the information on their website and do some observing right here in Baltimore. Okay, now we do my segment called News from the Universe, December 2015. Our top story tonight, ancient dwarfs tell tales of the olden days. Now, you might be thinking that this is yet another description of another sequel to the Hobbit movie, a movie that was probably twice as long, or maybe 3 times as long as it should be anyways. You could get Balin and Oin here telling tales for hours and hours more, I'm sure. But that's not what we're talking about here. These aren't the type of dwarfs we're talking about. What we're talking about are stellar dwarfs. So a star like our sun, maybe a little bit larger than our sun, goes through its hydrogen burning phase, hydrogen fusion phase, which is its main sequence lifetime. And then when it runs out of hydrogen, it starts to fuse helium in its red giant phase, and it swells up. And it runs out of helium, and then it actually blows off its outer layers in a planetary nebula. And whoops, get back. All right, in a planetary nebula, and what's left is the core of the star, which is called a white dwarf. This is a stellar remnant. It's the burnt out cinder of a star. It's very hot and it's very small. Very hot being bright and white, small being a dwarf. Hence, white dwarf, okay? So these white dwarfs are old dead stars. Our sun is going to live for about 10 to 12 billion years before it becomes a white dwarf. So if you see a white dwarf, it's evidence of an older stars. These are the stellar remnants, okay? Now, if you're looking for old dead stars, something that's lived 10 or 12 billion years, within a spiral galaxy, you want to look in the center of the galaxy, what we call the bulge of the galaxy. Okay? We believe that in these spiral galaxies, these bulges form first. Right? These are the stars that form initially, and then the spiral disks around them form afterwards. Okay? So if you're looking for white dwarfs, you might find them in the bulge of the galaxy. Well, within our galaxy, we don't see our galaxy as beautiful as this. We see our galaxy edge on, and we have done studies of our galaxy. So here is the plane of our galaxy here. Here is the galactic center. I keep hitting the wrong button, sorry. And Hubble has done some studies in this region here called Bade's window on what we call the sweeps field. And so this is not the full sweeps field. This right here is the sweeps field here. So this is Hubble's view of a very dense stellar environment toward the bulge of our galaxy. Now, SWEEPS is an acronym for Sagittarius Window Eclipsing Exoplanet Survey. So what did we first look for in this SWEEPS window? Eclipsing exoplanets, right? And so the first result we came from this SWEEPS image was, of course, finding planets around other stars. These planets that pass in front of their stars, and we saw the brightness go up and down of those stars. And so here's a number, I don't know, it's about 15 or 20 of these exoplanets found in this one patch of the SWEEPS survey. But we've made use of this survey over and over again. And the next press release I found about this was that we then looked for things called blue stragglers. Now, blue stragglers are a very particular type of star that shouldn't really be there. In an old star field, you should have mostly yellow and orange and red stars. But you find some blue stars, and these are evidence, we believe, of stellar collisions. Okay? So finding blue stragglers in the bulge field was a really cool thing. And now we've taken the original SWEEPS field and we've added to it some more data. The original one was from 2004. We have some 2011 to 2013 data, so we have much larger view. And we're looking at these region toward the bulge of our galaxy. And what we've done is we've taken two images that are 10 years apart. And with Hubble's fine resolution, we can actually measure the motions of these stars over the course of those 10 years. And in doing so, we can separate out the stars that we believe are in the disk of our galaxy compared to the stars we believe are in the bulge. And we identified the stars in the bulge, and of those bulge stars, we were then able to identify a population of white dwarfs. Now, these are small, very faint stars, but being able to pull them out tells us about the population from which they came. Because you're looking at the stellar remnants. It's like you're able to look at the tombstones of a town that lived long ago. We're able to look at the tombstones and actually then extrapolate back to the population. All right, and so what we were able to do with this was we were able to then pull out the hottest white dwarfs and take a population and able to study them. And what we got from them is actually that we confirmed our idea that the bulge does form first. It appears our bulge of our galaxy formed in less than 2 billion years. Now, I know 2 billion years sounds like a long time to you and me, But in terms of our galaxy, that formed first, and then the disk of material, the disk stars, then formed afterwards. So we're confirming our ideas that the bulge formed relatively quickly in about 2 billion years. We also got another result that appears to be a larger number of low-mass stars in the bulge compared to the disk. Now, I'm not really sure what this means just yet because we don't have a full population to really study. They're going to continue to do this. They're going to work with other telescopes to try and get more and a larger population. But from it, we're able to look at these stellar remnants, these old dwarfs, and from them read the history of the very earliest formations epochs of our galaxy. Second story, getting the cold fuzzies. All right. So I'll explain what I mean by that in just a second. The story is actually about Pluto and Charon. Okay, and we know the New Horizons mission went by in July and got some amazing images. This is sort of the standard one you see for Pluto. This is the standard full-face image you see for Charon. And actually, these aren't the full resolution. Okay, if you zoom in, you see all sorts of cool detail on Pluto. You see all sorts of cool detail on Charon. Of course, this is what we got for the face that we flew past during the encounter. But New Horizons did a buzz flyby. It didn't do a orbital mission. So we got one side in great detail, and I was talking with people the other day going, all right, well, what is it? They were trying to say, well, how come we don't see the other side? I said, well, we have images of the other side, but they're not going to be anywhere in great detail. Fortunately, on November 20th, the New Horizons team released those images. So what they released, and we're going to start with Charon here, is a full rotation of Charon. Both Pluto and Charon rotate in 6.4 days. So we got images of them in the week or so in advance and afterwards. So we got to see the all the sides of them. But of course, we only got to see the encounter side in great detail. So here is Charon, here's the encounter side, and here is the far side. You can see it's not quite the clarity there. Matter of fact, you can see there's almost a very distinct line from where we have really good data to where we have much less quality data. All right? They released the same thing for Pluto. Here is the encounter, and here is around to the backside. Okay? So here is that same comparison of the incredible detail we have on the encounter side and the not so great detail we have on the far side. Or I could say it's looking at Pluto's backside, because if you notice it's got this little dimple here, you know. All right, so this is why I called this story The Cold Fuzzies, because these objects are really, really cold, and unfortunately they are fuzzy. And even more unfortunately, we will not get any clearer pictures of these probably in our lifetimes, okay? We had one mission to Pluto. It got one side of it really, really good. I got one side of Charon really, really good. But your textbooks are always going to show the encounter sides. I don't think your textbook should include these as other things, but if I know textbook manufacturers, they're going to choose the coolest pictures. And also it allows me to say that, hey, I won't see you until after the new year, and I hope that your holidays are filled with the warm fuzzies. All right, so tonight our featured speaker is Lucy McFadden from the Goddard Space Flight Center, and she has much too long and distinguished a career for me to go through it all, but basically she says she studies the solar system's small bodies, SSSBs we sometimes call them in astronomy. I've seen that abbreviations. She is the co-investigator for the NASA's Dawn mission, and she was also the co-investigator for the Deep Impact mission that went to Comet Tempel 1. She was a member of the science team for the Near-Earth Asteroid Rendezvous mission, which landed a spacecraft on the asteroid Eros in 2001. So she's basically been involved in most of the cool space missions you've heard of, or going to the asteroid belt and such. She has also collected meteorites on the Antarctic search for meteorites, and participated in the Alamacita meteorite expedition in the Nubian desert of northern Sudan in 2009. That must have been an interesting adventure. You'll be honored to know that asteroid 3066 is named asteroid McFadden in her honor. And she was just last week elected by the American Association as a fellow of the American Association for the Advancement in Science. Okay, so with that kind of prep, you're gonna the pressure's on, ladies and gentlemen. Dr. Lucy McFadden.
Thank you, Frank. So let me power up here, and I think I hear myself amplified. Thank you very much for inviting me tonight, Frank. I'm excited and honored to be here and to have an opportunity to share with you my adventures in exploring the two main large asteroids in the main asteroid belt, asteroid 4 Vesta and the dwarf planet Ceres. And I hope you'll enjoy this journey of discovery as I have over the past almost more than a decade now. So to set the stage, I want to start with this view of the solar system. Just sit back and take a gander at this and immerse yourself in our solar system. So I'm only talking about, I'm a provincial astronomer, I call myself, because I only limit myself to our backyard in our solar system. And we are exploring asteroids in the main asteroid belt, which resides between Mars and Jupiter. And here we're looking back from beyond the asteroid belt and looking into the sun. And there's Mercury, Venus, Earth and its moon, and Mars. And our Dawn mission was designed to take us back to the early solar system, because we know that these fragments, these hundreds of thousands of asteroids in the main belt, were growing into planets, but the migration of Jupiter from the outer solar system into its current position resulted in a gravitational perturbation that disrupted the planet forming that was going on between Mars and Jupiter. So we wrote a proposal, the Dawn science team and my colleagues. We wrote a proposal to NASA in the mid-1990s to go explore these asteroids, and we were turned down. We wrote it again, and I think by the third time we wrote it in 1999, we finally were selected to continue developing our mission concept, and we were given the go-ahead to go in to build the spacecraft and execute our mission in 2002. So we won the Dawn mission. We had the mission. We had funding, and prior to building the spacecraft and executing the mission, we took advantage of the great telescope that's orbiting around the Earth and is managed here at Space Telescope Science Institute. Took advantage of Hubble and imaged both Ceres and Vesta as often as the telescope allocation committee would give us time until we got to both Vesta and Ceres. So on the left, it was the Hubble observations in 2004, or was it earlier? It might have been some earlier ones when we recognized. No, it was the 2004 observations when my colleague Peter Thomas at Cornell University measured the axial ratios, the equatorial and the polar diameter ratios, and combined with its density, which we know from perturbations by Mars and other spacecraft in orbit around Mars, we know its density, and determined that the relationship between the shape of Ceres, it looks spherical to our eye, and its density suggests that it's not a homogeneous body, but it's differentiated. So it has a core probably a rocky core, and given its density, which is 2.1 grams per cubic centimeter, where the density of pure ice is 1 gram per cubic centimeter, and the Earth's crustal material is about 3.3 grams per cubic centimeter. So an object with the density between 1 and 3 must have a significant amount of water ice as part of it. So it was Hubble observations that made us realize that Ceres was differentiated, which is one property of a planet. It's got enough mass and some interior composition and something heating it to cause the heavier material to sink to the center. Now, let's look at Vesta, which had been observed prior to 2007. In the 1990s, early 1990s, it was also observed. And early observations showed that Vesta is not circular, it's not spherical, it has this bite out of the bottom, which my colleague Peter Thomas, again from Cornell, and Rick Binzel at MIT postulated was a big basin from an impact. And so we knew that Ceres, which here is smaller than Vesta, these relative sizes are real, that it was a rocky object all the way through, had a big gouge out of it in the southern hemisphere, and it's this shape that makes that makes Vesta still an asteroid and not a dwarf planet. So one of the characteristics of being a dwarf planet is that it has to be spherical, and Vesta is not. So we had some knowledge, a lot of which was acquired from Hubble observations as well as years of ground-based observations of these two objects, what they're made of, Vesta being predominantly rocky, Ceres being rocky and icy together. And we wanted to explore we wanted to expand our knowledge of these objects to determine what it would tell us about planet-forming processes. They're small, they're not big like planets, so what's the difference? What are the similarities and differences between them, between these small guys and the large planets of Earth, Mars, and the Moon? Our mission is enabled by ion propulsion. So this mission was pretty spectacular because, very special, it was the first interplanetary mission that Americans flew that used ion propulsion. Now, ion propulsion is, we have a tank of xenon that gets accelerated through magnetic fields to be ionized, and that gets pushed out the back of the spacecraft. And if you remember back to early physics that you learned, for every action there's an equal and opposite reaction. So if you push ions out this way, the spacecraft is going to be pushed in the opposite direction. And it was a constant low magnitude of an impulse of the ion engines, something that gives the force of my hand on a piece of paper that results in the propulsion of this spacecraft. So over and over, integrated over and over time, these little pulses have projected this spacecraft, the Dawn spacecraft, out to the asteroid belt. The trade-off is that it only took 100 kilograms of xenon as opposed to maybe 500 kilograms of conventional hydrazine propulsion. This allowed us to launch on a low-cost, lower-energy rocket and allowed us to get there. That was the good part about it. It allowed us to go out to the asteroid belt. The downside was that it took 7 years to get there. Okay? So we had to be patient. So the Dawn spacecraft has thrust for 50,000 hours. Anyone want to convert that to years, approximately? 5.7 years. And with each thrust, the spacecraft is accelerating. So it's the fastest spacecraft in the solar system. Can you believe that? But I think that's true. So then we are powered. All the power for the spacecraft comes from these beautiful solar panels. And notice the person here for scale. 65 feet long. To put that in perspective, when I moved from Baltimore in the early 90s, my household goods fit in, along with 2 other households, in a moving van that was 70 feet long. So this is about the length of a large moving van, tractor trailer. And they have to be large. There has to be a lot of space, a lot of volume, surface area, because we're far away from the sun and we have to gather enough energy from the sun to power the spacecraft and the instruments. We have a suite of instruments on board. We have a primary camera, which was built by our colleagues and partners at the German Space Agency called DLR, the German Aerospace Agency, and it's operated at the Max Planck Institute for Solar System Research. Andreas Natu's pictured here is our team lead. We have our American instrument built at Los Alamos National Lab, led by Tom Prettyman of Planetary Science Institute. It's a gamma ray and neutron spectrometer, measures the elemental abundance of emitted neutrons and gamma rays from the surface. And then we have a visible and infrared mapping spectrometer provided by our partners from the Italian Space Institute and led by Cristina De Sanctis in Institute for Astrofisico in Rome. And then actually our 4th instrument is the antenna on the spacecraft itself. I don't have a picture of that, but we get gravity measurements. We measure the gravity field and determine the mass based on the position of the spacecraft as it orbits the asteroids. And slight motions tell us about the strength of the gravitational force of both Vesta and Ceres. And so that the antenna relays back the information on the position of the spacecraft. So that's actually an instrument as well as a communications device. So we launched on board the Delta II rocket at Cape Canaveral. This is an actual picture at the launch site. Have any of you been to a launch down at Cape Canaveral? If you ever get a chance, isn't it amazing? I mean, this is an actual picture at night, the night before we launched. So these are lit up. It's not. This is not a model. We were there checking it out. I have mosquito bite from remnants from that. So be sure to take your DEET. So we checked it out. We got to go see that everything looked okay. But what do we know? We only know about what's up here in the nose cone. But nevertheless, we had to go out and check it out and be there to see it. And then the next morning at dawn, September 27th, 2007, the spacecraft launched, and it was a spectacular sight. To be equal, only outpaced by the Deep Impact mission that I saw launch a couple of years before. Although, how can I tell which was more exciting? So here's our roadmap. We're now looking down on the sun from above. So here's the sun with the dotted lines or the paths of all of Earth and all the planets. So we launched in 2007, and with our ion engines, we can change our trajectory because there's little jets that can change the direction. And so we orbited out, spiraled out from Earth in an ever increasing and accelerating trajectory. Flew past Mars, where we turned on our instruments and checked it out, made sure everything was working as we hoped and expected, and it was. And then continued out to Vesta in 2011, where we went into orbit. So we did little epicycles all around here until till the end of I think we got there in May and ended August of 2012, if I recall, and then out to Ceres. We got to Ceres in March. So let me give you I'd like to give you a summary of what we learned at Vesta in the past couple of years. So Dawn's the first mission to orbit a main belt asteroid, and this is Vesta on approach, but I want to show you that the next one has a movie and shows the whole summation of a year's orbit. So I want to point out some things on Ceres here. It's dark up at the pole because we got there in winter and never got good viewing geometry. Note these striations here going across the equator, and then there's some more over here. They actually correlate with impacts down here in the southern hemisphere. So look at this. This is the shape that we saw from Hubble's telescope. We saw the two bites out of we saw what we thought was one bite out of at the southern hemisphere. And it turns out that these are actually two overlapping craters. Okay, and this is so cool, so we'll look at it again. So the two craters in the southern hemisphere, here's our snowman. At Christmas time, we put a Santa Claus hat on it and said Merry Christmas from the Dawn team. There are craters all over the place. Seems like in the north it's more cratered than in the equatorial region, and then this mountain in the bottom, at the southern pole, is from the rebound from the impact, and it was rebound from that giant impact. Now, let's take a look in a different perspective. That's enough of that. I can watch that for a long time, but we want to go home tonight. So here's a view of the south pole of Vesta, and the colors represent heights from a mean geoid, a mean sphere. So the range goes from minus 14 miles at the bottom, which is the blue, the deepest part, to 12 miles high. And this rivals that. It's twice as high as Mount Everest. That shouldn't surprise us because Vesta has a diameter that's the width of the state of Arizona. So we really are looking at a really tiny body with very little gravity. And if you have low gravity and you get hit and you get an impact, of course it's going to eject material and it's going to fly. It will escape the gravitational grasp of Vesta very easily. And in fact, we don't have a record of this impact, so we turned to our artists. And so it was a huge collision that probably happened. Now, the science team, we have debates over this. It either happened 1 billion years ago or it happened more like 4 billion years ago. And there are two different models published in the literature with the time frame for this. But we do know that the collisional ejecta from this impact sent many asteroids into another orbit that's similar to that of Vesta. So there is a family of Vestoids that exists in the asteroid belt. And furthermore, there's some of the smaller fragments from these asteroid families have impacted the Earth. And in fact, 1 out of every 7 meteorites found in our Earth meteorite collection does come from Vesta. So we know that. How do we know that? Someone asked, and we knew that before we went there. We know that when you shine reflected light, when you take light and reflect it on meteorites such as this is called a basaltic achondrite meteorite. And when you shine sunlight on it and measure the reflected light, passing it through a prism, it gives you a spectral fingerprint of these meteorites that is identical to that of Vesta itself. And that spectral signature of Vesta has only that spectral signature of Vesta and the Vestoids, the asteroids that have a similar orbit to Vesta's. So there's one line of evidence. But then another colleague at MIT did some dynamical modeling and found that the position of all these Vestoid asteroids sort of is like, leaves a trail from Vesta's orbit itself back toward a resonance with a resonance that clears any asteroids from the area. And when material gets into that resonance, it gets sent into an orbit that crosses that of the Earth. So we have a dynamical model as well as this physical evidence that these guys come from Vesta, that these meteorites come from Vesta. That gave us a huge advantage because we know a lot about these meteorites because we can study their chemistry, their isotope abundances, their radiometric ages. So we can study these in our laboratories on Earth. And then we had the opportunity to put this information into a big geological context of Vesta itself. Okay? So now, with the Dawn spacecraft, we now get to see the spatial, we get to look at Vesta as an object. We get to map it. We get to put cartographic coordinates on it. And then the geologist started looking at the surface features and drawing in boundaries for different regions and different epochs, different times in the history of Vesta. I'm going to start in the upper left and note that the green areas, the Marcia crater, I have to practice it with my Italian accent, Marcia crater, these three snowmen crater, is the most recent, the youngest material, or the youngest feature on the surface of Vesta. And we know that because there are very few craters on top of it. It's a large area, it's fresh. Then we go back to when this impact formed, their material came from beneath the surface, so there's dark material around it. And then it goes back through different colors. We get to the Rhea Silvia formation, which was this the most recent large impact crater down in the southern hemisphere. And then we go back to the Venenea crater, which is harder to see. It's the remnant. It's underneath the Rhea Silvia impact basin. Here's the Venenea basin here. So we have a geological time frame and different epochs of events that the geologists prepared for us. Then I want to show the albedo map. That's the brightness map. Comes from the word alba, which is white in Greek. So the albedo is a measure of the whiteness or the brightness of the planet. And here we go from reflecting 15% of the sunlight that hits it, so that's the dark region, up to as much as 40% of the sunlight that hits it. And you'll see that there's this dark region here between between 60 and 180 or 200 degrees longitude. We knew about this dark region from our ground-based telescopes, but we didn't know what was causing it. Why is one hemisphere dark and the other is lighter? I think we've solved that, and I want to sort of show you I want to show you the combination of our results from different instruments that give us a clue. Okay, so this stuff's dark. The next I'm going to show you a map of the type, those basaltic achondrites, those meteorites that I told you. Those meteorites come in 3 different flavors. E for eucrite, H for howardite, D for diogenite. They are all related, but this dark material here is ancient crustal material that has not been covered over by debris from these impacts down the southern hemisphere impacts. So this is ancient crustal material that we call eucrites. Then next I want to show you our elemental map from our gamma ray and neutron spectrometer. And the scale is a little bit different, but you can see that the regions here shown in blue is about this 60 degrees to 200 degrees in longitude. And here, this is shown blue is material that's rich in hydrogen. And what does that tell you? What common compound do we know, other than hydrogen itself, do we experience and know of frequently that has hydrogen in it? Water, thank you. Good. So these guys who mapped it said, oh, there's an excess of hydrogen in this region, an excess of hydrogen in that dark region. And the gamma ray guys say, well, usually when there's hydrogen, that means that there's water or something water-like. It's bound, the hydrogen's bound up in some water molecule or compound. So then the spectroscopists came up with the definitive evidence that this dark region, here it's shown blue for water, is associated with a mineral that has water bound in its structure. So here I have to show you a squiggly line. It's a spectrum, and I hope you'll bear with me. But the fingerprint, this is really a spectral fingerprint showing that material in the blue, it's plotted here as blue because it comes from this region, has an absorption band that at this wavelength, 2.8 microns, that is associated with hydrated minerals. And when we look at other regions outside that are not in this blue region that's outside here, that's more yellow or green, that absorption band is not as strong. So this material is hydrogen-rich, water-rich, and darker than other regions. And our conclusion, what we think, is that that these basin-forming impacts redistributed the material on Vesta, that the dark material, hydrated, carbonaceous material, we call it carbonaceous because material in the meteorites is this carbon-rich material that's also has carbon and clays, is remnant from an earlier impact. And it's probably remnant from that first impact that formed the Venonea Basin. But when Rhea Silvia came and hit, it didn't obliterate all of the debris from the first impact. And then also from our gravity measurements, we determined that Vesta has a metallic core. And that's very significant because the Earth has a metallic core. And Vesta, too, differentiated. It was heated up, and the heavier materials sank to the center, and we have a metallic core with a rocky mantle and this crustal surface material that's like the basaltic achondrites, which are basalts, like volcanism, like volcanic rocks on the Earth. So here, Vesta has many similarities to small Earth-like planets. Okay? That was our hypothesis going in, and we came out with specific evidence that we didn't anticipate, but specific evidence that points to a sequence of events that produces Vesta as we know it today. So let's go on. So that's a summary of Vesta, and we just got it published, finished our publications. They came out this fall. So our team of about 100 people spent 3 years analyzing the data and publishing in a whole suite of publications that you can find by going to Google Scholar and search on Vesta and plus Dawn, and you can tackle it in first primary research. So we left in 2002, and remember I said it takes long, it takes patience. Well, it's 3 years of putting through the main asteroid belt to get from Vesta to Ceres. And okay, so then I said to myself, okay, I better tell you guys what I was working on specifically. I was responsible for the search for moons around both Vesta and Ceres. I want to go through this a little bit quickly. It's partly, we searched and we didn't find any. Neither Vesta nor Ceres have any moons. hey, what's with that? Pluto. And furthermore, Max Muchler helped me search, both using Hubble telescope and with the Dawn spacecraft. And Max was part of the team that found 5 moons around Pluto. And yet, there are none around Vesta or Ceres. So one approach, and I want to tell you, we feel like we've been there in space when we're searching for these moons. Here's an approach image. This is Ceres. This streak, one might get excited and think that it's a tail of a comet, but no, it's the readout of the digital camera, and it doesn't clear itself enough, so it's an artifact of the readout. But we take an image here on the left of a star field and look and see which stars we can find in our images, and then what we're looking for is something that's not a star, and then try and then see if we see it in subsequent images. So then what we do is we take subsequent images and we stack them up. And the spacecraft, remember, the spacecraft's moving. So if you're moving, you know what happens with your camera. It's blurry all the time, right? Well, we registered the images on Ceres, which we've put up here, and lined them all up. And all these streaks, this is not Morse code, but these are series of background stars, and they're all going in the same direction. So we're looking for something that's not going in that direction. And that something that's moving in a different direction but has a series of 4 dashes in a different direction could be a moon. So we see some individual dots. These are hot pixels, so they're artifacts. We see a couple of streaks that are going in a different direction, but none of them have this same set of 4 dashes. So anything that's real, that's associated with the motion of Ceres, would be going in a different direction. So we looked hard. We had experienced people helping us, Max, as well as Dave Skillman at Goddard, and we did not find anything. And then we determined what's the faintest thing that we could see, and assume that faint, if there were something, it would be as bright as Ceres, which, by the way, only reflects a little less than 10% of the sunlight that hits it. So we searched down to about between 30 and 300 meters in size. So there's nothing orbiting Ceres down to about 30 to 300 meters. So now let me go on to Ceres. Okay. So my story is not going to be complete, but I'll tell you what I see and how I see it so far. So this was March, and our rotation movie, and this too, planetary scientists love to watch things sit and spin. So we see, what do you see there? You see Christmas lights, okay. I have at Goddard, we have a counterintelligence guy, and I was talking to him because I just traveled overseas, and he said, a friend of his said, well, what are those headlights? He called the counterintelligence guy. And I said, look, as soon as I know what they are, I'll let you know. There are other bright spots too, though. Catch these guys. Where is it? There's some other bright spots. Those aren't the headlights. So there's multiple bright spots. There are also craters. But do you see any big basins like the Rhea Silvia impact basin? No. So we'll be counting craters and get some ages from the crater size frequency distribution. Then let's see, the size of Ceres, it's about the width. The diameter of Ceres is the same as the distance across the state of Texas. It's about 1,000 kilometers across. Its bulk composition contains about 25% water, and it may in the past have had a liquid ocean. Right now it's a warm, icy body. It's also partly rocky. It's not totally icy, and I'll tell you why I think that. And it only reflects 10% of light instead of about 38%. as Vesta does. So it's a lot darker than Vesta. And in fact, the dark material from Ceres could be similar to the dark material that hit part of Vesta. So now our geologists and mappers are making these maps. So here we have the bright spots, which we've named Okator, or the bright spots are in the Okator crater. All the features on Ceres are named after goddess of the harvest. So they're all harvest gods from different cultures. Here's another bright spot. I think it's called Hulani crater. And I'll show you a couple of other features in a minute. Here's Hulani crater, where the bright material has ejected and forms a nice ejecta blanket around the whole crater, and material fills in. You can see there's some structure here, some ridges, because the terminator is not quite smooth. And here's some other linear structures where there's collapse of crater walls or whatever it is. These are definitely tectonic features because they're changes in the structure of the surface. And then we have the Lonely Mountain. This was also in the newspapers. Here's this big mountain peak. It's it now has a name called Ahuna Mons. And if you look at it, it sort of has a flat top that's similar to the surrounding area in terms of, it looks like it's cratered, just like the surrounding area, but has these very steep slopes. And my postdoc is in the process has done some analysis of this, the structure and what mechanisms may have produced this structure. It's also superimposed on a topographic high, too. So this is 3 kilometers high, but this region around it is also higher than the surrounding area. And then we had an opportunity. So we got to Ceres in March. We did a survey orbit at about 4,700 kilometers altitude for a couple of months. Then we went to a lower altitude of 1,200 kilometers, I believe. And when we did that was called our high altitude orbit. We got a better view of the Okator spots, bright spots. We were able to determine that their brightness, their albedo, is about 50%. Okay? Whereas the background material is 9%. So it's 5 times brighter. And in the center, there seems to be a mound right in the central area. And then this is the second bright spot that resolved into about 8 other smaller spots. The crater walls are not perfectly round. They have some different structures to them, and here's some slumping on this crater wall. The wall failed. So this tells us that there is some strength on the surface, but it's not totally rocky like Vesta. Otherwise, the crater walls would be perfectly round. So Ceres is sort of halfway between an icy object and a rocky object. Because it can support crater structure. Now I want to show you recently released images and a map projection of both the north and the south polar regions of Ceres. On the north region here, we found another mountain. The viewing geometry isn't very good, but there's now 2 mountains on Ceres, Yosolo Mons and Ahuna Mons. You can maybe see, you have to use your imaginations, as will our geomorphologists. Although they'll have their tools, they'll be able to look at these structures in 3 dimensions and figure out is this part of a large basin? I think maybe. And what else can we see? Other crater walls, large craters, many mid-sized craters, and we can compare the number of craters of a certain size in the different hemispheres and see what that tells us. So there's a lot of data here that has yet to be analyzed. The dark material in the dark region in the southern hemisphere is again due to the seasons. Interesting thing about Ceres is that its polar axis is tilted very small, only 3 degrees. Whereas on the Earth is tilted 23 degrees, and we get our seasons because of the tilting of the Earth's axis. For Ceres, they get the seasons because the orbit goes below the ecliptic. So Ceres is down below the plane of the Earth and the Sun, and it goes down to 10 degrees below the ecliptic. So it's the viewing angle due to its orbit, not how it rotates on its axis. So we didn't get total coverage in the South Pole, but it's not that bad. Here we have our spectral images from our imaging spectrometer. We have a visible, an infrared, and a thermal infrared image. And these are 2 different regions. And this is telling us something. We don't have this quite analyzed completely, but I want you to appreciate that here's the Okator bright spots. It's bright in the visible. You don't see it much. There's not much contrast in the infrared, which is beyond where our eyes can see. And then out here in the heat region, in the thermal infrared, the Okator bright spots are cooler than the surrounding material. So they're very bright, but they're cold. Now look at this region, which is the Helani crater. It's bright in the visible, like Okator. It's bright in the infrared, totally different than Okator. And it's hot in the infrared. So the composition of these bright spots, they both look the same in the visible, but the infrared tells us that they're not the same material. They don't behave the same. That's a challenge that the Dawn team is currently working on, trying to figure out what materials could be, what's the nature of the 2 different materials of these bright regions. So there's now my story. My story isn't complete because we're still an active mission. I'm coming up to the end, but I want to tell you about the fact that we believe that the surface, from our spectroscopic results, looking at the total global surface, we don't see any evidence for water ice on the surface. Okay? No water ice. That's pure H2O ice. But we do see spectral features that are consistent with ammoniated species. So there's an absorption band that is attributed to ammoniated clays. Now that's sort of hard for me to get a handle on, but clays are sheet-like structures that have water between the sheets. On Ceres, there's water, but there's also ammonium ions in those interleaved, in those interlayers. And there's information about that coming out in the December 10th issue of Nature, where the data from the Dawn mission has expanded on what we knew from ground-based observations prior to getting to Ceres. So we have new interpretations of the surface, the global surface composition coming out in Nature next week. But with the presence of this ammoniated species, it lowers the temperature at which water will melt, or icy bodies will melt. So you can get a liquid material beneath the surface, and you can get things that will fluidize beneath the surface. But this ammonia, where does this ammonia come from? It's not stable in the region of the main belt. If you put ammonia on the surface, and actually if you put water on the surface, it will sublimate. So it won't remain on the surface as pure water or pure ammonia. But out beyond the planets, out in the Kuiper belt, nitrogen-bearing and ammonia-bearing ices are stable. So if we have ammonia-bearing species here in the main belt, we are hypothesizing that it either had to have, that either Ceres formed out here in the Kuiper belt and migrated inward to the asteroid belt, or small particles and frost ammonia ices were migrated in, were contaminated in the early solar system when the nebula was gas and dust and still forming. But in any case, the ammonia species, which is stable out here when it's not bound up into the interior of an object. So those are that's our puzzle. You know, where did this ammonia-bearing species come from? How did it get there? What is it telling us about the formation of the early solar system? And we have two similar but slightly different hypotheses that we're working with. And where are we now? We have, here's these different altitude orbits that I was talking about, so I can check the numbers that I recalled. So our survey orbit was about 5,000 kilometers. High altitude was about 2,000 kilometers. And we are now, the spacecraft is now spiraling down from the high altitude orbit. And each of these, each color, each groove on this record is an orbit representing the change from high altitude down to the low altitude orbit. And on December 15th, 2 weeks from tomorrow, we will get down to our low altitude orbit, where we hope to get higher resolution spectra of the bright spots, so we can hopefully see some spectral signatures that will allow us to discriminate between the bright material on Ceres and the rest of the body. And we hope to get some compositional information about this mountain, the mountains that are formed, and compare them to the global spectra. The state of the spacecraft is healthy. However, we are watching our fuel levels. This diagram here on the right represents the amount of fuel that has been used, amount of the xenon. We're down here to, actually, this is actually the fuel use for the hydrazine, because we have a spacecraft that's slightly handicapped. It's been in space for 7 years, and its attitude control, it's getting a bit shaky. Its attitude control, 2 of its reaction wheels, which control its stability, have failed. And so, we need 3 axes to remain stable. So we're now using hydrazine to keep it stable for that 3rd axis of stability. But we want to make sure we don't use up all the hydrazine. So here our tank is half full. And when we get down to low orbit, we're going to use the hydrazine more, because we want the spacecraft to be steady so that our pictures are stable, so we don't get fuzzy pictures. Then we're going to write a proposal and compete with the New Horizons mission and say it's more important to get funds to stay in orbit around Ceres, because we expect to learn X, Y, and Z that will be more important than what the New Horizons mission says. So maybe while NASA headquarters managers are making their decision, we could do a public outreach one at the same time, and don't let the NASA managers see what the public thinks, and see if their results are the same. And there are others. It's not only between the 2 missions. I think there are 2 others that they have to deal with. So this work is a team effort. Our email distribution goes to 120 people around the globe. and we have a lot of fun. We're like family because we've been working together since before 1999. We even clean up well and take our awards at the Smithsonian. This was for Vesta. I don't know what award they're going to give us for Ceres, because I think Ceres is way cooler than Vesta. We have our websites for more information. We keep posting and updating and releasing our images. So please do watch our websites with our blogs. Our chief engineer has a great dry sense of humor. He does write a blog, so it's filled with numerical facts that are interesting and obscure. So everything's named after goddess of agriculture, and we did find one thing on Earth that looks like the mountain Ahuna Mons. But now I can't figure out whether this is a photoshopped mining talus or whether it's real. So anyway, I think with that I'll stop and take some questions. Thank you.
Thank you so much. We were just chatting about it online. It's just the folks are finding it so great that they're getting the latest solar system science from one of the primary scientists involved in the mission. They're just really happy to be able to get this.
I'm happy to be able to do that, to share it.
Questions? Now, anybody in the back? I always start down front.
You know what? Can we do? And what I like to do. Excuse me for interrupting.
Well,
no. But would you mind alternating between taking a question from a woman and taking a question from a man?
Okay. I will stop soon then.
I know. Well, we'll keep doing. You don't have to follow that, but I do that to encourage the women to think of some questions.
I haven't seen you here before. Are you new here tonight?
I've been here before.
Okay, great. But anyways,
when a spacecraft is in the main asteroid belt, is there any significant risk of getting hit by an asteroid?
I think you said the operational term, any significant risk, and I think I can answer that. It's not a very significant risk. We have not been hit by anything that we could detect. And I like to defer to my chief engineer, who really cares about the spacecraft, and it's his job to keep it safe. And when we went to Vesta, we said, well, we want to look for moons just to make sure that the spacecraft isn't going to run into something that we don't know about, because that would be embarrassing. Then he said, when we got to Ceres, he said, this is really for science, because we're not going to run into anything there. So the fact is, space is pretty vast, and fortunately, I haven't been proven wrong by being hit by anything that we could detect.
Right. I mean, but that is a strong fallacy that gets out there, is that the asteroid belt is crowded with asteroids all over the place. If you remember a certain Star Wars movie, promulgated that misconception. If you go see Pixar's latest film, The Good Dinosaur, the whole opening sequence is just, again, lots and lots of asteroids all banging into one another, looking really, really close
but if we
together.
went to the movies and it were realistic, it would be really dull.
It would be boring. If they represented the way it was, you wouldn't see another asteroid. You couldn't possibly see another asteroid from one asteroid. So down front here. I didn't see any ladies first? Okay. Oh, there we go.
Yes.
Sorry, then you're next.
When you were in charge of finding moons, was it very disappointing to you that there weren't any on either of those?
Yeah, absolutely. I mean, because I would have made the cover of Nature magazine. Right? So yes, it took a lot of determination and stick-to-itness, right, to write the paper, to publish it. But I said, well, wait a minute. There's a story in everything, right? And so I finally thought about it when I got to the bottom of my doldrums, because I didn't discover anything. I have to write a paper about no moons. And so I said, well, wait a minute, what's that telling us? And then I said, wait a minute, there's around Vesta, there's a family of asteroids around Vesta. We see these impact basins. The surface is cratered by impacts. Why isn't anything stuck in its orbit? So I wrote the paper, Vesta's Missing Moons. and someone, and I published, how we searched for it, and I raised the question, and I said, and I got a dynamicist who really thought about something and came up with, well, maybe there's this resonance there. Oh, he found another asteroid that had a resonance, so maybe that sort of prevented anything from staying there. But the probability of creating a moon around something, unless it forms like the Earth's moon, is pretty slim.
Right, but we were chatting about this also online, that 3 of the 4 largest Kuiper Belt objects have moons, right? Whereas the 2 largest asteroids don't. And the only asteroid I know that has a moon is Ida and Dactyl.
No, there are hundreds.
Hundreds?
There are
Okay,
hundreds of
The only
asteroids
one that's
with
been
moons.
publicized, obviously.
But they're smaller asteroids, and it's just not fair that the Kuiper Belt objects have moons and the big main belt asteroids don't.
Okay, now for Hunter.
Assuming your research was not an end to itself in terms of understanding the early solar system formation, finish this question. Now that we've established Vesta has similarities to Earth and there's ammonia on it, therefore that tells us that our early solar system was...
It tells us that the processes that are active in planets were also active in small bodies, in bodies that are orders of magnitude smaller than what we call planets. So what does that tell us about the early solar system? Thank you for asking that question. You're pushing me to my end. That I think, again, I can't prove this, but to complete the story, the early solar system formed, or the solar system formed from a rotating disk of gas and dust. And we're still, the process of forming planets when material collided and stuck and grew is a very hand-waving process. Now, a lot of people do calculations to try and get that process going. But we've identified a time that's 4 billion years ago where the conditions were such that we get differentiation. Things will melt. You get accumulation of enough stuff that radioactive decay will heat up these objects and form little planets. So I think planetary activity occurs across a wider size range than we thought previously. How's that? Is that okay?
Okay, we have a more in green.
How is the Dawn mission planned to end? Because the way you talked about it seems that, Dawn is just the spacecraft just gonna orbit around Ceres and somehow it's gonna run out of fuel, or like.
Yeah, you're right. I didn't talk about how it's going to end. And it's so funny. I took my daughter to a launch once, and she saw the rocket go up, and she was 7, and she looked at me and she said, "Mom, is it going to come back?" And, I never told her what was going to happen, so I'm sorry that I didn't finish. Because Ceres has water somewhere beneath the surface, we have to, the planetary protection officer,
This is a real officer now.
yeah,
Okay?
who we really want to respect because we don't want to contaminate a place that might have life. If you've got water, there might be life. So we have to be very careful. And so she's in charge, and it's my understanding that she has told us, or the planetary protection regulations say that you have to be in an orbit that's stable for 300 years. So we will park the spacecraft in an orbit that is stable for 300 years. Now, there's a good thing about that, though. We can then use it as a relay station. If we send something back, we can then use it to relay information back.
Okay, Peter.
What do you think the object was that slammed into Vesta? Was it another asteroid?
I think it was another asteroid that was probably a carbonaceous chondrite, which is another type of asteroidal material that formed under cooler temperatures and never reheated. Never either grew big enough to get enough heat to melt, and was made of material that condensed at colder temperatures from the solar nebula. So and most of the meteorites, they're called carbonaceous chondrites. They have a lot of clays, a lot of dark dark material, and they're just condensed at a lower temperature in the solar system. So it's a different type of material. And we have a lot of it in our meteorite collection. So it was a dark carbonaceous material.
Okay, there's a woman in black in the back corner.
So I'm puzzled why parking something for 300 years is going to protect the planet. I mean, like, that seems very arbitrary.
Yeah, by 300, and I don't know the answer to that, what the rationale was, but I guess,
It's going to park for 300 years, it might go for 3,000.
well, right, I think it was sort of, policy. You understand policy, right? You want something that will reasonably protect the body from, these man-made contaminants, but it's also sitting out in space where nothing's going to grow. So it's a very good question, and I know you're a historian, and the historical answer is what you're looking for, but I'm going to have to look into that. Because, 3,000 years, that's not reasonable for us to, who knows whether man will be here in 3,000 years. We'll probably be living there. So we don't want to make it too constraining, but also likely that we won't mess things up.
Okay, all the way in the back.
You mentioned the molten or the metal core, but nothing about molten rock. So I was just curious about any kind of evidence of possible magnetic fields or anything like that.
Oh, thank you for asking that question. That's a very painful question for my principal investigator, Chris Russell, to answer, because when we first proposed this mission, we had a magnetometer on board, and it was his instrument, the magnetometer, that got thrown off for budgetary purposes. So we had no magnetometer to determine whether there's a magnetic field associated with Vesta, and because it's got a metallic core, it might. It probably isn't molten because Vesta's just not big enough to have enough insulation to keep the core molten as the Earth's core is.
And that's required for a magnetic field, isn't it?
Motion, but there could be a remnant magnetic field.
Does Mercury have a remnant?
Absolutely, and so does Mars.
Right. So it might be like Mercury or Mars in terms of just having a frozen-in magnetic field.
Yeah.
Let's see, down front here.
How did you get the spacecraft to slow down enough to drop into orbit?
It doesn't slow down. We're spiraling. We're spiraling out, and we sort of sidle up to it and
You
start.
actually trailed it or something, come up behind it.
Yeah, and we are accelerating to get out there, but it doesn't. I don't think it slows down. We match the orbit. So.
Yeah,
But we are going out.
This
We're
is what
going faster.
But getting into this orbit required the ion engine, right? The other.
The
Without the ion
hydrogens.
engine, they wouldn't have been able to get into this.
Well, we wouldn't be able to get anywhere. So we're accelerating away from the sun. So we have to overcome the gravity of the sun, and then match the orbit. So it's a dance, and these guys can play with the orbits. And in fact, we had an anomaly, and we had to, when we got close to Ceres, I've almost forgotten about this. Something went wrong, and the spacecraft went into safe mode, and so the navigators, so these guys that are space navigators, they had to figure out a trajectory, where to give it commands to turn it on, and which engine they turn on when, and they had to loop past. We had to fly past. We were going too fast. And we had to go out beyond and miss it, and then turn and then change directions and come back into orbit. So it all comes from cruise control.
So, can you imagine a kid out there watching this going, I could grow up to be a space navigator?
Celestial dynamics.
Other questions? Do we have any women who have questions here tonight? All right, we don't, so let's go there, because I don't think
I'm curious about the cost since the conception of the mission to building the spacecraft and then now acquiring data and docking it for 300 years or so. What is the cost, I guess, human hours versus material?
Oh, the people are cheap, paying us. It's the guys that build the spacecraft. Most of the cost is in building and testing, making sure that all the parts work and that there's no failure. But the scientists, our budget goes up before launch, and then after launch we have to maintain, but it drops and then it stays stable. And then the scientists come in and it keeps going down, and then at some point we have to turn it off.
So it's in billions, or?
Oh, it's, no, the Discovery missions are of $250 million range. That's without the launch vehicle, though. And it's over 10 years. I had a friend of mine over there. We have to.
Sorry, friend
I was
first.
just wondering about the spectroscopy. You said you saw hydrogen and you saw carbon, and you said it was hydrated carbon. How do you know it wasn't a hydrocarbon?
Well, because those have little wiggles in a slightly different part of the spectrum. And in fact, there are, in the Ceres spectrum that's going to be published shortly, there is a region in the 3 micron region where we do see organics, CH bonds. But we just can't say much about them, so we will point to them. So they are there.
Okay, there's a question down here.
You were getting CO signatures, so that means at least some asteroids have oxygen.
There's oxygen in absolutely, all rocks have a lot of oxygen in their structure, in their crystal structure, but not free oxygen, not O2 like we can breathe in the air. It's structural, oxygen in the structure between the silicon and in the silicon tetrahedra with oxygen. All the rocks are made of silicon dioxide or silicon tetrahedra. So there's a lot of oxygenated species.
Okay, other questions? You had one. Here we have.
I was interested in the fragments that you found on Earth, and pardon me, I know this is near and dear to your heart, but I can't remember if it was Ceres or Vesta, but were the fragments you compared when you reflected the light from them?
That was Vesta.
Okay, thanks. So was it, have you broken it down to find out what minerals are in it? I was just interested more in that.
Absolutely. The minerals are predominantly pyroxene minerals, which is again a certain crystal structure with a range from magnesium-rich mafic silicates called orthopyroxene, and a range that goes through clinopyroxene and plagioclase too, which is an aluminum calcium silicate. They are minerals that are found predominantly in volcanic rocks, rocks that have been heated to the melting point of these silicates and then cooled slowly enough to have a crystal structure. And there are no meteorites that are similar, have the same spectral signature as Ceres. That's also a puzzle. So we don't seem to have Ceres fragments in our meteorite collection.
Yeah, I hadn't heard the term Vestoids before, but that makes
that's the family of asteroids near Vesta.
Herman.
Frank, hi. Lucy, I don't want to put you on the spot, but have you ever seen Vesta with your own eye through a telescope?
Yes.
Good.
I looked at it. Oh, through a telescope, absolutely. Oh, yeah. My first publication in 1978 was of a Vesta from a telescope.
And
I thought you were going to ask me if I'd seen it with my naked eye, because Vesta is magnitude, its apparent magnitude is about 6.5 or something. And if you know where to look, and you have good eyesight, which I don't have anymore, you can see it with your naked eye without a telescope. And I have pointed out and sat there with a map and sort of tried to see it.
Same question for Ceres.
Ceres, no. Ceres is fainter. It's further away, and it only reflects 10%. So I've seen it through a telescope.
That's what I'm asking.
But not with my naked eye. Yep, from Mauna Kea. That was fun. Thanks for letting me remember that.
Okay, last two questions here and then here.
Yeah, what propelled you personally towards study of research within the solar system? Was it more attainable discovery as opposed to deep space, or was it something else?
No, it was happenstance. So when I was an undergraduate at Hampshire College in Amherst, Massachusetts in the early 70s, I made a list of classes that I wanted to take, and I couldn't find my list. I was running out of things that I wanted to take. My 9th choice was astronomy. And I was given 3 classes, and my first 3 choices, this was the late 60s, early 70s, right? My first choice was political justice, dimensions of consciousness, and film workshop. And so did everybody else want to take those, and so I got astronomy. But then it was just, and then I went to graduate school and I said, oh, I want to study these neat stars, these peculiar stars. And my thesis advisor said, I study the solar system. I don't know anything about that. So you better find something in the solar system. There's a lot to study.
Well, I certainly hope a wildly successful career is enough consolation prize for you. For not being able to take the courses you want.
I was hooked. I mean, I got hooked after that.
All right, last question down here.
The representations we see of the asteroid belt show it to be fairly dense. What are we talking about in practical terms as the average distance between each of the asteroids, and do they typically exert a gravitational effect on one another?
So, well, that was a homework question on my when I taught the solar system, and I can't remember the answer. I had to go look at my notes.
It's about, if you think of the largest, the reasonable size asteroids, I don't know, like 100 meters or above, a kilometer size above. I think it's about 1 million miles apart. Okay, yeah. That's a rough number.
They do exert a gravitational force on each other, though.
If you're on one, you couldn't reach out and touch another one. How far apart's the next one?
A million miles.
1 million miles.
1 million miles.
Oh,
1 million.
Yes.
But they still exert a gravitational force on each other, and then it's a question: can you calculate it? Sometimes you can, because by some close approaches, and sometimes you can't. Most of the times you can't.
All right, that has been a fantastic talk tonight. Next month, hold your applause a second. Next month, we have Vanessa Thomas sitting back there, Max Mutzler sitting there, Rosa Diaz sitting somewhere else, talking about White House Astronomy Night. Hope to see you all there. One more round of applause. Thank you.
Thank you. You're a great audience. I appreciate it. Enjoyed it.
Yes. Okay, so stars in the densest regions of our galaxy, they get down to they would get down to